We introduced previously the operational amplifier and some of the applications, and we considered the ideal case of the operational amplifier. The only non-ideality, I would say, that we considered was that the open loop gain A may be finite, not infinite. In the ideal case, A is infinite. In real op amps, A is finite. Maybe it's usually a large number, maybe 5,000, 10,000, 100,000, 200,000. Now we will consider the effect of finite bandwidth, and this is kind of surprising. What you see is the body plot of the open loop gain. So this A is the open loop gain of the op amp, the A that appears in the equation V3 equals A times V2 minus V1. So this is the open loop gain. And this is the body plot. So A in dB starts at 100. 100 dB is 100,000 volt per volt. So that's a pretty large A. Of course, it's not infinite, but it's 100,000, so very large. The surprising aspect is that at some very low frequency here, 10 hertz, the gain starts to drop. The open loop gain starts to drop at this very low frequency. So this A looks like a low pass single time constant transfer function with a 3 dB frequency of around 10 hertz. It drops with a slope of minus 20 dB per decade or minus 6 dB per octave. And it has an FT. FT is the frequency at which the gain becomes 1 or 0 in dB. The FT is around 1 megahertz. This example is from a real operational amplifier, one of the most popular and successful op amp circuits called D741. So in fact, A is not infinite, and not just that, it's finite, and the value of A drops very quickly with frequency. So A at 10 to the 4 hertz is like, what is it, like 40 dB, less than 40 dB. At 10 to the 5, less than 20 dB, 20 dB. So the gain drops very quickly. It's reduced by a factor of 10 every time the frequency is multiplied by a factor of 10. We can model this, and we should study how this affects the gain of the popular inverting amplifier configuration and non-inverting amplifier configuration. What happens to the gain there when A behaves like this? So to model A, it looks a lot like a LPSTC, just low pass with one very, very, very dominant pole at 10 hertz. So we can say A is the low frequency value, AM. AM is like, if this is 100 dB, then this should be 100,000 volt per volt. 20 log 100,000 would be 100 dB. Divided by 1 plus S over omega 3 dB, and omega 3 dB is 2 pi times 10, because this is 10 hertz here. And that's in radians per second. And omega T is given by this equation for low pass single time constant. Omega T would be square root AM squared minus 1 times omega 3 dB. But because AM is very, very large, 100,000, when you square it and then you do a minus 1, The -1 basically disappears, and the square root of AM squared minus 1 would be just AM. So AM times omega 3 dB, this is 100,000. This is 2 pi times 10. And therefore, this is 2 pi times 1 megahertz. So that's the 1 megahertz here. Okay, so this is the model of how the open loop gain changes with the frequency. Why does it do that? The 3 dB frequency is very, very low. We've seen examples of circuits where the frequency drops, but not at frequencies that are so low. The reason is related to a topic that we will study later in the course. It's the stability of the circuit. The op-amp, because it has such a very high, very large open loop gain, and it is used in circuits that have feedback in them, what may happen is that the op-amp could potentially become unstable. What does this mean? Let's look at a very simple example. If I take an op-amp and connect it like this, this is the voltage buffer circuit, where the output is equal to the input. If you take a regular op-amp where A does not drop at such low frequencies, even if the input is grounded, and in this case, according to the equation of the circuit, the output should be 0. Even if the input is grounded and you have this feedback from output to inverting input, you may get some oscillations at the output. So we're getting an output when there's no input. We call this, these oscillations, we call them an instability. This is an instability. The circuit is unstable. It's producing an output when the input is 0. And we will study when and why it does that when we study feedback amplifiers. But for now, what we need to know is that one way to fix this problem, if I'm building a buffer and the input is 0, I don't want any output. I'm not building an oscillator to get a sine wave. I'm building an amplifier, a buffer, and if the input is 0, the output should be 0. So if I want to maintain this and make sure that the output will be 0, I will not get a sine wave out of nowhere. I have to stabilize the circuit. So how do we stabilize the circuit? One way to stabilize the circuit is actually to destroy the open loop gain. How do we stabilize the circuit? By destroying the open loop gain. We do that. We introduce this very low frequency pole. So by introducing this very low frequency pole, we can show, and we will do that later in the course, that after adding this, so we actively add a component, maybe a capacitor, to the circuit to create this pole, so that the open loop gain starts to drop at such a low frequency. If it does that, then we can show that this will never happen. If the input is 0, the output will be 0. So we stabilize the circuit by sacrificing the open loop gain. We don't sacrifice it all the way down to very, very low frequencies to DC, but we start sacrificing it starting some low frequency like 10 Hertz, and it drops at this rate of -20 dB per decade after that. So this F3 dB is made very low, and we make it, the circuit designer makes it very low. It's not like a parasitic capacitor that is there and it's annoying us. No, the circuit designer adds a component, usually a capacitor, to the circuit, so that we get this very low frequency pole that will sacrifice the open loop gain at higher frequencies. And this will assure us that the circuit will be stable, so it doesn't produce an output if there's no input. Let's see the effect of this on, say, the inverting op-amp amplifier circuit, this one, where the gain was minus R2 over R1 if A is infinite, but now A is finite and it's an A of S, changes with frequency. So the expression that we derived previously, if A is finite, is the following: minus R2 over R1 and divided by 1 plus R2 over R1 over A. But now A is an A of S. So I'll take the expression from the previous slide and plug it here. AM over 1 plus S over omega 3 dB. And I get this expression. Now AM is this 100,000, it's very, very large. So this would be very, very small. If 1 plus R2 over R1 is 100, and you divide by 100,000, this is 10 to the minus 3. So that's negligible compared to 1. I can easily neglect this. So I get minus R2 over R1 divided by 1 plus S over omega t divided by 1 plus R2 over R1. And I can, after I neglect this, I can say that it's like a low pass, single time constant behavior. And the 3 dB frequency for this amplifier, this one, is omega p, which is this. Omega t over 1 plus R2 over R1. Omega t is the frequency that corresponds to 0 dB gain, and it's AM times omega 3 dB. So that's omega p. All right, so the low frequency gain for this amplifier is minus R2 over R1, expected. But now this amplifier has its own 3 dB frequency at omega t over 1 plus R2 over R1, or in megahertz, 1 megahertz divided by 1 plus R2 over R1. So we can show the body plot for this amplifier with R2 over R1 equal to 10. So this is VO over VI in dB for this amplifier, 10, take log base 10 of 10, that's 1 times 20 dB. So I have 20 dB at low frequency for this inverting op-amp circuit, but this doesn't continue forever, right? Because now this circuit has a 3 dB frequency, which is 1 megahertz divided by 1 plus 10. So a bit less than 100. So 100 would be here, and omega p or FP would be here. So after this frequency, it drops because the equation, the transfer function is a low pass STC. It drops with a slope of minus 20 dB per decade. So this is how the fact that we introduce this very low frequency pole in A is how it affects the inverting op-amp. The inverting op-amp would now have a bandwidth which is around 100 kilohertz, and that's not too large. And if you look at if you consider the gain versus bandwidth, FP is 1 megahertz divided by 1 plus R2 over R1. The low frequency gain is minus R2 over R1. So in absolute value, it's R2 over R1, volt per volt. So it looks like if I consider the bandwidth and the gain, the product is almost constant, not exactly constant, but almost constant. And if I increase one, the other will have to drop. And if I decrease one, the other would increase. So if I increase the gain, I make R2 over R1 20, the bandwidth would become 1 megahertz over 21. If I make this 50, the bandwidth becomes 1 megahertz over 51. And they go in opposite directions, and their product is almost constant. So the gain bandwidth product is almost constant. And if one increases, the other decreases. And this is a trade-off that you can use if you want a certain amplifier, an inverting op-amp amplifier, and you need large gain, don't expect a lot of bandwidth. If you want a lot of bandwidth, large bandwidth, then you would have to accept lower gain. And graphically, we can see this here. So this is the 20 dB. The 20 dB gives me around 100 kilohertz. If I increase to 40 dB, then I get around 10 kilohertz. If I increase to 60 dB, I get around 1 kilohertz. So if I increase the gain, the bandwidth decreases, and vice versa. If I decrease the gain, the bandwidth can increase. And the product of gain and bandwidth is almost constant. Now let's look at some limitations also in real amplifiers when we talk about large signals. The first one is something that we've already seen, and that's output voltage saturation. So in output voltage saturation, this is when the output voltage, once it reaches the supply levels or close to the supply levels, starts to clip. So the output voltage saturates at maybe a volt or down to a few millivolts within the supplies. So this is a limitation. You cannot have very large outputs. The output voltage will clip at almost supply level, and that will create, of course, distortion. There are also limits on the output current. So consider this op-amp. This is part of a circuit, and it may source or sink current. So it may give a current to a certain load that's connected, or take current from the load. And there are limits on how much current it can source or sink. So in the two directions, there's a limit of maybe a few milliamps or a few tens of milliamps, 10 milli, 20 milli, 5 milli. It cannot, the op-amp cannot give an unlimited current. So here, if you have a very small resistor, say 10 ohms, and here you think that you will have an output which is 10 volt, that's impossible, because this implies that the current flowing here is 10 volt over 10 ohms, and that's 1000 milliamp. And this is much, much lower than the limit. So this means indirectly that this cannot happen. If you have a 10 ohm load and your limit is 10 milliamp, then what you can hope for here would be 0.1 volt. That's it. Because 0.1 volt is 100 millivolt divided by 10 ohms. That's 10 milliamps. That's the limit. There is also another limitation called the slew rate. The slew rate is the maximum rate of change possible at the output of the op-amp. So there is a limit on the maximum of the output voltage, and the slew rate is a limit on the maximum, not output voltage, maximum rate of change of the output voltage. So derivative of V out of T. So there is a maximum for V out of T, and there is a maximum for V out, dV out by dt. There's also a maximum for that. So let's do an experiment and see how, where and how we can see this. So again, we will use this buffer, and we expect the output to be equal to the input. We apply at the input a step of height V volt. So you see the Vi of T is a step. At T equals 0, it jumps from 0 to V. What should be the output? Well, VO is equal to VI. And if I just use the mathematical equation, at the output, I should see the same step. In reality, what happens? In reality, we get this. We don't see a step at the output. We see something that looks like a straight line with some finite slope. And then once it reaches the V level, it stays there. So the output, therefore, cannot rise faster than this rate, than this slope. And the slope of this line is called the slew rate, and it's the maximum rate of change. The output cannot change faster than this. If you try to make it change at a rate that is faster than this, you can't. That's a limitation of the op-amp. This is extremely fast, infinitely fast. In 0 time, you jump from 0 to V. So that's infinitely fast. And you try to do the same at the output, it cannot rise infinitely fast. It can't even rise this fast or this fast. If there is a slew rate limitation, the fastest rate would be this. So a slew rate, for example, may be 5 volt per microsecond. And this is it. The output voltage cannot rise at a rate that's faster than that. So if V is 10 volt and the slew rate is 5 volt per microsecond, it will take the output 2 microseconds to reach the 10 volt. And it won't reach the 10 volt in 0 time. So this is the slew rate, the maximum rate of change at the output of the operational amplifier. Now we may think that this may be due to the A of S, that A has this very low 3 dB frequency. So let's see if this is the case. For a voltage follower, if A of S is AM over 1 plus S over omega 3 dB, the transfer function for the voltage follower due to A of S being some AM over 1 plus S over omega 3 dB. For the voltage follower, this is what we get. 1, at low frequency, it's 1. And it continues to be 1 until omega t, and then it drops with a slope of minus 20 dB per decade. So this is what's happening inside the operational amplifier if I'm considering that the slew rate limitation may be due to this. The input is a step, and for a step input, I'm going to use Laplace domain analysis here. So this is the input, and this is multiplied by 1 over 1 plus s over omega t. So this is vi of s times the transfer function of the follower. So this is t of s, and vi of s is a step, so v over s. So that's the Laplace transform of the output. And if I do inverse Laplace, I get vo of t, which is 1 minus e to the minus omega t times v. All right, so how does this look like? This looks like a saturating exponential, an exponential that rises towards v. So the y-axis here is v out over v. The x-axis is time. So this rises towards 1. Vo approaches v as t goes to infinity. But is this the behavior that we're seeing with the slew rate? No, not really. Because if we compare this with what we see, the slew rate, in some cases, maybe like the red line here. And if you observe the output of the op-amp with a step at the input and considering that A of S changes with frequency, we will not get the exponential. We will get something like this. If the slew rate limitation is this, we will get something like this. If the slew rate is the light blue, what does this mean? It means that we will not be slew rate limited. It means that the output, this one, is rising, but we're not facing slew rate limitations. So we will see the exponential because the exponential is rising at a slower rate than the maximum allowed. So that's fine. We will see the exponential without any change. But if the slew rate is this, the red, then we will be limited by the slew rate until the rate of change of the exponential becomes less than that. And then it becomes kind of similar to an exponential. So the conclusion is this slew rate limitation is not due to this. If it's due to this, then we should always see the exponential, no matter what. But it's not. We don't always see the exponential. It's something else. There's something else in the circuit that's limiting the slew rate. So what is the impact of slew rate? Why do we care about it? Actually, the slew rate causes distortion. If you have a sine wave at the input, you expect a sine wave at the output, and you may not get it because of slew rate. So if the output, if the input and the output are supposed to be sine waves, we will have slew rate limitation when dVo by dt approaches slew rate, right? dVo by dt is slew rate. This is the limit. If Vo is Vo max sine omega t, the maximum rate of change dVo by dt max would be Vo max times omega. So this is the slew rate. This is the equation here. If I have a sine wave, then the slew rate, the maximum rate of change of the sine wave is omega Vo max. And this now gives me a limit on omega. And we call this the Ful-Power Bandwidth. So omega times Vo max equals slew rate gives me a maximum omega that I can use if I want to avoid distortion. So the full power bandwidth would be the slew rate divided by VO max times 2 pi. That's the full power bandwidth. Any frequency that's higher than this will cause slew rate distortion. The output will no longer be a sine wave, even if the input is a sine wave. It will start to look more like a triangular wave. So the op-amp distorts, stops behaving linearly. Here's an example. Say the slew rate is 1 volt per microsecond. So the op-amps are specified. We were given the slew rate for the op-amp in this case, 1 volt per microsecond. So in 1 microsecond, the voltage can change by 1 volt. And the output has a maximum of 10 volt. So this means that the full power bandwidth would be 1 volt per microsecond divided by 10 volt into 2 pi, which is 15.9 kilohertz. So any frequency that's less than 15.9 kilohertz can have an output which is 10 volt max and will not be slew rate limited, will not be distorted by slew rate. Any frequency that's higher than 15.9 kilohertz, if it wants to reach 10 volt at the output as a maximum, it will be distorted. It will not be a pure sine wave. Let's see, for example, at around 80 kilohertz, what happens. At around 80 kilohertz, I cannot reach 10 volt without distortion. How much can I reach? I can use the same equation and say the maximum that I can reach in the output. So if the output is supposed to be a sine wave and I want to keep it clean without distortion, what would be the maximum in this case at 80 kilohertz? I can also use the same equation, but now find VO max. And VO max will be slew rate over 2 pi times 80 kilohertz. So that's 2 volt. If the output increases more than 2 volt, it will be distorted. Let's do an example where I have a circuit. Circuit is this, an op-amp. Minus plus 100 ohms. This is the input. This is grounded. This is 1K. VO. And there is a resistor from the output to ground here, which is 500 ohms. So the specifications are for the op-amp are the following. VO is between minus 10 volt and plus 10 volt. So the output voltage is limited to 10 volt plus or minus. The output current IO is limited to 10 milli plus or minus 10 milliamp plus 10 milliamp. So this can be in the two directions, but the maximum in the two directions, either like this 10 milli or into the op-amp 10 milli. And the slew rate SR is 10 volt per microsecond. The question is, what is the VI? Okay, so VI is given to sine what is it? 2 megaradians per second, 2 sine omega t. Omega is 2 million radians per second. And this is in volt. VO is VO max sine omega t, should be kept undistorted. So we want to avoid, should not be distorted. We want to avoid distortion. And the question is, what is VO max? So how much is this? All right, so let's see. Let me modify the question because, okay, now what is the value of VO? But VO is not given that, it's a sine wave. Okay, so this is from a previous midterm. Yeah, the question is find the maximum value of VO, just that. Okay, find maximum value of VO. Okay, so I want to find the maximum value of VO given 3 limitations. This, and this. VO should be between -10 and 10. IO should be between -10 and 10 milliamp. And the slew rate is 10 volt per microsecond. And the input is 2 sine omega t with omega equal to 2 megaradians per second. Okay, so I have to consider the circuit and the limitations in the circuit first. Let's see what kind of circuit is this. This is an inverting amplifier. And the gain is VO over VI is minus R2 over R1, where R2 is 1000 and R1 is 100. So this is R2 and R1. So that's minus 10 volt per volt. The 500 ohm at the output does not affect this calculation. It's like a load. And even if you connect a load, the gain would still be minus R2 over R1. So if I consider this and assuming that I have no limitations whatsoever, VO should be minus 10 times 2 sine omega t. So assuming no limitations, minus 20 sine omega t volt. So this is the first limitation here. It's obvious that this VO max would not allow this. Since VO should be between minus 10 and 10, this is not possible. 20 sine omega t is not possible. So we will not be able to reach 20 volt. So maybe we can reach 10 volt. So this implies that VO max is possibly 10 volt, and then we saturate. But we have 2 other limitations. Let's look at the slew rate. Slew rate, I think we can quickly find the limit for slew rate because it's a simple equation. Omega omega times VO max is slew rate. Omega is 2 million radians per second. 2 million times VO max, the value that we will get if we are slew rate limited, is SR, 10 volt per microsecond. 10 volt per microsecond is 10 to the 7 volt per second. 10 to the 7 volt per second. 2 million is 2 times 10 to the 6. So what do we get here? This means that VO max is 10 to the 7 over 2 times 10 to the 6. So that's 5 volt. So slew rate will limit me to 5 if I want to avoid distortion. It can go above 5 if I'm okay with distortion, but this is the limit if I want to avoid distortion. So there's still one more. So we check this, we check this. Let's check IO. IO is flowing in here. But remember that there is a virtual short between these two. And this means that if the op-amp is still operating linearly, the 1K and the 500 ohm kind of appear in parallel. So IO splits and flows in 500 and in 1K, and the 500, it goes to ground, and in 1K, it also goes to ground. So 1K and 500 appear in parallel. So for the IO limitation, IO into 500 parallel 1000 is VO. And this means that VO max is IO max into 500 parallel 1000. So this is 10 milli into 500 parallel 1000 is 333.3. And this is therefore 3.33 volt. So the output limit in volt on VO is 10. If I consider the output limit on current, it's 3.33. And the output limit to avoid slew rate distortion is 5. And if I want to consider the circuit overall now, all the limitations that I have, I will take the minimum of the 3 limits. So the current will limit me to 3.33, and therefore VO max in this case is 3.33 volt. If I limit myself to just 3.33 volt, it means that the output will be distorted because the input is 2 sine omega t. And if the situation is ideal, the output should be 20 sine omega t with a minus sign, but it's limited to 3.33. So it will be pretty distorted, and the distortion, the limitation, is on a maximum current in this case.